Number 1, prove that x plus y squared minus x minus y squared equals 4xy for all real numbers x and y. So to prove this, we're going to start with one side of the equation and make it look like the other side. So clearly you can't do much with 4xy, so let's start with that side of the equation. X plus y squared minus x minus y squared. What does that equal? So this is where that whole idea of look for and make use of structure comes into play, because I have something squared minus something squared. In the last lesson, we talked about the difference of perfect squares. So we can apply that identity to simplify this expression as x plus y, the first thing, plus the second term, times, we can factor this as the first term minus the second term. So you could go through, you could do this whole problem by squaring each of those binomials and then subtracting, you're going to get 4xy. But here's where that looking for and making use of structure makes things a little bit easier. So x plus y plus x minus y, well, that's 2x, y minus y is 0. Over here we have x plus y, distribute the negative 1, minus x plus y. We have 2x times x minus x is 0, y plus y is 2y. 2x times 2y gives me 4xy. So we showed that x plus y squared minus x minus y squared is 4xy. I want to get a note on how I started with the left-hand side and did a bunch of steps to get the right-hand side down here. I didn't set up this original equation and just do algebra and say, yes, it equals 4xy, yes, it equals 4xy. Pick one side, make it look like the other. Number 2, prove that x cubed plus a cubed equals x plus a times x squared minus ax plus a squared is an identity. So I need to pick which side I want to start with. Clearly, we're going to start with that side because there's nothing I can do to x cubed plus a cubed. X plus a times x squared minus ax plus a squared. So we're going to multiply. You could do it with a table, but to make this look like a nice proof, I'm going to use the distributive property. I'm going to distribute x plus a in. So x squared times x plus a minus ax times x plus a, and then plus a squared times x plus a. All I did was I distributed an x plus a into that trinomial. And now I'm going to use the distributive property 3 times. X squared times x is x cubed. X squared times a is plus ax squared. Minus ax, I'm distributing a negative ax. Negative ax times x is minus ax squared. Minus ax times a is minus a squared x. And finally, a squared times x plus a squared x. A squared times a is plus a cubed. So if you did this in the table, you would see that you had those exact 6 same terms. Now we're going to combine like terms. Nothing else is x cubed. I have an ax squared minus ax squared. That's 0. I have a minus a squared x plus a squared x. That's 0. So we're left with x cubed plus a cubed as we desired. Again, notice how I started with one side, made it look like the other side. Number 3, Mr. Hines was exploring the following statement. The sum of the product of 3 consecutive integers and the middle integer is the cube of the middle integer. He began filling in the table below. Complete the table. Okay, so let's read through this statement again. The sum of, so I'm adding 2 things together here. The product of 3 consecutive integers and the middle integer. So if I take the product of 3 consecutive integers and the middle integer, the sum of those 2, do I get the cube of the middle integer? So 1, 2, and 3, those are 3 consecutive integers. So the product is 6. 1 times 2 times 3 is 6. If I add the middle integer to that, if I add 2 to 6, I get 8. Well, 8 is 2 cubed. 2 is the middle integer. 8 is 2 cubed. Is it the middle integer cubed? Yes. 3 times 4 times 5. 12 times 5 is 60. 60 plus the middle one is 4. 64. 64 is 4 cubed. Yes, that holds. So if I do 2 times 3 times 4, that gives me 24. Now I want to take that and I want to add the middle integer to it. So that gives me 24 plus 3, which is 27. We know that 27 is 3 cubed. So the statement does hold again. 4 times 5 is 20, times 6 is 120. I want to add the middle integer to that. I got 125. Is that the middle integer cubed? Well, what's 5 cubed? That's 125. So the statement looks like it's true. The statement looks like it's true. Now let's prove it. So prove the identity from exercise 4. The sum of the product of 3 consecutive integers and the middle integer is the cube of the middle integer. So let's convert that statement into algebra first. We need to convert that statement into algebra. And I gave you the hint of let x be the middle integer. So let x equal the middle integer. So I need the integer before that and the integer after that. So what's one integer before x? That's going to be x minus 1. So the first integer. And if you did one after that, that'd be x. 1 after x is going to be x plus 1. That's the third integer. If you did this by doing the standard consecutive integer setup, x, x plus 1, and x plus 2, you get the same answer. You just have to do a little bit more work. So the product of those three, so we claim that the product of those three plus the middle one, which we said was x, is the middle one cubed. So we claim that that polynomial identity is true. So now let's prove it. So our proof, we're going to start with x times x minus 1 times x plus 1 plus x. Again, just start with that side. I need to multiply those two together. First, I'm going to notice x minus 1, x plus 1, that's the difference of perfect squares. You could go through multiply it out using the table or the distributive property, but it's the difference of perfect squares. Now I'm going to distribute that x in. X cubed minus x plus x. We get x cubed. So the proof of this wasn't that hard, but setting up, converting the English into the algebra was the trickier part for this question. 5. Is x plus 4 squared equal to x squared plus 16 an identity? Justify your decision. So an identity is something that's always true regardless of what x I plug in. So hopefully you don't make the mistake that 9th graders make in Algebra 1 and say, oh, x squared, 4 squared, x squared plus 16. Hopefully you know that's not true. Let's justify why. One way we can look at this is we can say, what is x plus 4 squared? That's x plus 4 times x plus 4, which is x times x plus 4 plus 4 times x plus 4. So that gives me x squared plus 4x plus 4x plus 16, which is x squared plus 8x plus 16. Clearly, that does not equal x squared plus 16. So this is not an identity. Isn't it an identity? No. Why? Because x squared plus 8x plus 16 is not x squared plus 16. Prove that a triangle with side lengths x squared minus y squared, 2xy, and x squared plus y squared, where x is bigger than y is bigger than 0, is a right triangle. So to show that something's a right triangle with its 3 side lengths, I need to show that those 3 sides satisfy the Pythagorean theorem. So, is x squared minus y squared squared plus 2xy squared, does that equal the third side squared? Y squared squared. So I'm going to start with this side. X squared minus y squared squared plus 2xy squared. What does that equal? Well, to square a binomial, we came up with that identity in class today. You square the first term, and then 2 times their product, so minus 2x squared y squared, and then you square the last term, so plus y to the fourth. Plus, well, what's 2xy quantity squared? Well, that's 2xy times 2xy, which gives me 4x squared y squared. I'm going to go through and combine my like terms now. Combine my like terms and see that x to the fourth, there's no other x to the fourths, minus 2x squared y squared plus 4x squared y squared is plus 2x squared y squared, and then there's no other y to the fourths. Now maybe you're stuck at this point. Maybe you're stuck and you're not really sure where to go. Whenever we get to that point, go over to the side and look at the other one. Look at the other side of the equation. X squared plus y squared squared. That's the quantity, square the first, plus 2 times their product, and then square the last. Aha, notice that's what I wanted. So, our final proof is, because I know x squared minus y squared squared plus 2xy squared equals x to the fourth plus 2x squared y squared plus y to the fourth, we showed that that is equal to x squared plus y squared as we wanted. Okay? So whenever you get to a crazy algebra proof like this and you're not sure where to go, start with one side, get as far as you can go. Maybe you realized you could factor that, and that's great if you realized you could factor that. If not, go to the side and see what you want. I want to get x squared plus y squared squared. That's what it's equivalent to. And then finally, there's our proof right there. I showed that that's x to the fourth plus 2x squared y squared plus y to the fourth, which is equal to that expression there. Review questions. Factor the following difference of perfect squares. So 25x squared minus 4y squared. That's 5x squared minus 2y squared. So that factors into 5x minus 2y, 5x plus 2y. Maybe you have 5x plus 2y, 5x minus 2y. The commutative property says that those two are equivalent. Notice in the second part of this question, I have something squared minus something squared. Look for and make use of structure. So it's x plus 2 plus y plus 2, the first thing plus the second thing, times the first thing minus the second thing. We need that parentheses there because I need to distribute that negative. So I get x plus y plus 4 times x minus y plus 2 minus 2, which gives me 0. So that expression factors into x plus y plus 4 times x minus y. Again, that's the important idea of looking for and making use of structure. 8, factor completely. 125 minus 8x cubed. So hopefully you notice that this is 5 cubed minus 2x quantity cubed. So we can use the difference of perfect cubes identity and say that this expression is equivalent to 5 minus 2x times the first term squared plus their product plus second term squared. And then we know that we can't factor this expression anymore. Alrighty, b, x to the sixth minus 216y cubed. So hopefully you said, oh wait a minute, that's x squared cubed minus 6y cubed. So we can apply, again, the difference of perfect cubes formula here and get x squared minus 6y times the first one squared, well, x squared squared is x to the fourth, plus their product, so 6x squared y, and then the second term squared, plus 36y squared. Can I factor x squared minus 6y anymore? No. Compute this quotient using the reverse tabular method. So I'm asking you to do the reverse tabular method. You could do this with long division, but it's good to be good at both methods. So x cubed divided by x gives me x squared. So I'm going to have a quadratic polynomial as my answer. So x squared, x, and then the number, the constant term. So 2x cubed, 3x squared, minus 23x, and then negative 12. So I know a 2x cubed had to be in that box. What times x gives me 2x cubed? 2x squared. 2x squared times 4 is 8x squared. But I only want 3 of them, so what plus 8x squared gives me 3x squared? Negative 5x squared. Negative 5x times x gives me negative 5x squared. So I have a negative 20x in that box. But I want negative 23 of them, so I need another negative 3x. Negative 3 times x gives me negative 3x. And that gives us the negative 12 as we wanted. So what is that quotient? That quotient is 2x squared minus 5x minus 3. Number 10, write a fifth degree trinomial. Write a fifth degree trinomial where the leading coefficient is 7 and the constant term is 6. So this is just vocabulary here of polynomial functions. Fifth degree means I need to have x to the fifth be the highest power. It needs to be a trinomial, so I need 3 terms, where the leading coefficient is 7. The leading coefficient is in front of the highest power. It's the coefficient of the highest power. So I need a 7x to the fifth, and I need a constant term of 6. So that means I need to have the number in that polynomial is plus 6. So this would be good, but I asked for a trinomial, not just a binomial. So somehow you need to make this a trinomial, so I add a plus 3x squared. You could put whatever thing you want in there, as long as its power is not x to the fifth. It needs to be x to the fourth, x cubed, x squared, or x, and our constant is 6. So this was just reviewing polynomial vocabulary.